Okay, we're now recording. So we're going to try to cover a lot of ground today on curve sketching. Okay, so 4.3, I only did, I think, one problem. Okay, now 4.3 and 4.5 are both curve sketching problems. Sometimes they can get long, okay, admittedly, okay? But it's the same concept for pretty much all of them. Okay, so we'll be doing all the tests that we said yesterday. So I can't keep track of all that. That's okay. You can put it on your cheat sheet. Again, it's the kind of thing where you have to do the homework. If you do the homework, you do enough problems of it and say, oh yeah, I get the idea. I know what I'm supposed to do now. So, so my job is to show you a whole bunch of problems with that. Okay, and I do, we do have an advantage that they're taped. Everything is taped. So if you think I'm going too fast or you're covering too much material, that's intentional. I want to cover a lot of ground, and you can always go back and look at the videos. And that's one nice advantage of the way that we're doing it now is we have a chance to always go back and look at the videos for these. Okay, so a lot of our section is curve sketching. You'll be seeing me bounce around. I may bounce around problems in 4.3, but it's intentional. The author has put some of the problems in such a way where it's actually better if I bounce around for some reasons because of the curve sketching problems are similar or the difficulty is a certain level. And likewise for 4.5. So 4.3 and 4.5, I may be jumping back and forth. It's all pretty much curve sketching. Okay, then of course we have to come back for 4.4 from there. Okay, and again, in our schedule, we were supposed to do 4.3 for today and tomorrow, I guess. So we'll see how it goes. All right. Let me show you what some of the problems look like. Okay, so 9 through 17, finding intervals where f is increasing or decreasing, find local max and min, concavity, inflection points, all that stuff. Okay, so it's all based on the information I gave you yesterday. And here we go. So most of today is going to be doing a lot of curve sketching problems. All right, so I'll start you off with 4.3, number 9. And yes, I realize maybe you can't see it because of the focusing thing. Try to adjust a little. All right, x cubed minus 3x squared minus 9x plus 4. And here really is the power of the calculus, where in pre-calc, how do you graph it? Well, I mean, besides using a graphing calculator, all you can do is plot a whole bunch of points, right? Plug in 0, 1, 2, 3, -1, -2, whatever. How do you know where there's a high point, right? How do you know where there's a low point, and so on? Well, now we have techniques to do that. Okay. So the normal thing you want to do for these kind of problems is take two derivatives. Immediately take first and second derivative. Okay, so f prime of x, 3x squared minus 6x minus 9. And whenever you can factor, you should factor. So factor out to 3, x squared minus 2x minus 3. And that factors further into 3 times x plus 1, x minus 3. Immediately find the second derivative. Okay, so double prime, 6x minus 6. And you don't really have to factor that. It's pretty easy to work with. Okay, now set f prime of x equal to 0. First derivative is right here. 3 times x plus 1, x minus 3, set it equal to 0. That's easy, -1 and 3. Okay. Now find the y coordinates. So y coordinate, you always plug back into the original. So -1 goes here, here, and here. Comes out to be -1 minus 3 plus 9 plus 4, which is 9. Okay. Put -1 there, that's -1. Put -1 there, that's -3. Put -1 there, it's plus 9 plus 4, so 9. Plug in 3. 27 minus 27, that's nice, 0. Minus 27, 9 times 3 plus 4, comes out to be -23. Okay, so my critical points are -1, 9, and 3, -23. Okay, critical points. You say, what is a critical point? Point where the derivative is either 0 or undefined. Here's a derivative. Derivative is always well defined. Okay, so these are the points where the derivative is 0. Okay, derivative is 0. From before, derivative is 0 means I might have a maximum or a minimum. Okay, so how do we tell? We do a sine chart. We've done sine charts before. So here's a sine chart for y prime, which is 3 times x plus 1, x minus 3. So on my number line, I laid down -1 and a +3. Okay. If I plug in -1, I get 0, right? Plug in 3, you get 0. That means everywhere else on a real number line, I do not get 0. So if I don't get 0, I get either a positive or a negative. So I determine, is it positive or is it negative? So I plug in. Okay, so pick something on this side of -1, -2. Something in the middle, 0. You could pick 1, you could pick 2. Something over here, 4, 5, 6, 80, 1,000,000, but 4 is good enough. When I plug in, I don't really care about the exact value. I just want the sign. Okay. Now, 3 is always 3. 3 is always positive. So see these pluses right here, plus, plus, plus? That represents the 3. That never changes, right? All right, -2. -2 plus 1, the sign is negative, SIGN. I don't care about the exact value. I just want the sign. -2 minus 3. Yes, it's -5, but it's negative. So essentially, I'm going to have a positive times a negative times a negative. That comes out to be positive. Okay, in the middle, 0. We already know 3 is positive. 0 plus 1, positive. 0 minus 3, negative. Positive times negative is a negative. So I put a minus sign here. And then this region, 4. 3 is positive. 4 plus 1, positive. 4 minus 3, positive. I'm going to have a positive times a positive times a positive, positive. All right, first derivative positive, increasing, increasing. First derivative negative, decreasing, right? From yesterday. Page 293. A, f prime greater than 0, same as slope positive, f is increasing. F prime less than 0, f is decreasing. Increasing, decreasing, increasing. All right, intervals of increase and decrease. So the function f is increasing from -∞ to -1, union 3 to infinity. So when is it going up? My abbreviation for increasing is an arrow going up, right? Very suggestive. You don't have to write INCREASING. As I move from left to right, it's going up. So -∞ to -1, union 3 infinity. -3 to -1, union 3 to infinity. Where is f decreasing? Only between -1 and 3. Okay. Decreasing from -1 to 3. All right, relative max and min. At -1, what do I have? The roller coaster goes up, then it goes down. That must mean we have a maximum here. Relative maximum. -19 is a relative maximum. You can say local maximum. Now, as long as I'm here, 3, -23 is a relative minimum. How do I know it's a minimum? Take a look at the sine chart. The roller coaster goes down, and then it goes up. So you have a minimum, right? That guarantees it. So -19 is a relative maximum or local maximum. 3, -23, relative minimum. What am I taking advantage of? This picture, page 294. right? How do I know I have a maximum? To the left, graph is increasing. To the right, graph is decreasing. B, relative minimum, local minimum. The graph goes from decreasing to increasing. And again, if I ever get these situations, I have neither a maximum nor a minimum. I'm done with the first derivative analysis. Now I do the second derivative analysis, and the second derivative analysis is almost identical to the first derivative analysis. Okay, set the second derivative equal to 0 also. So you know how over here you said set f prime equal to 0, blah, 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 do a sine chart. Second derivative, same thing. Set the second derivative equal to 0, blah, 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 do a sine chart. Okay, so where was my second derivative? 6x minus 6. 6x minus 6 equals 0. Simple algebra, x equals 1. Find the y coordinate, 1 comma negative 7. Plug in 1. You'll have 1 minus 3 minus 9 plus 4. If you work it all out, it's negative 7. So 1 comma negative 7. So on my number line, I lay down 1. Pick something here, 0. Pick something here, 2. Okay, the second derivative is 6x minus 6. Plug in 0. 6 times 0 minus 6, that's a negative. That's a minus sign there. So minus. Then I plug in 2. 6 times 2, 12. Minus 6 is 6. Positive. Second derivative negative, concave down. Second derivative positive, concave up. From yesterday. Page 296. A, second derivative greater than 0, concave upward or concave up. I'm usually just going to say CU. Second derivative less than 0, CD, concave down. Second derivative equal to 0, we found that out. We might have an inflection point. Okay. In order to have an inflection point, there has to be a change in concavity. So does a concavity change at x equals 1? Yes, it does. Either from concave down to concave up or from concave up to concave down. So I do have an inflection point. Okay. So we have everything analyzed now. So intervals of concavity. F is concave down from negative infinity to 1. F is concave up from 1 to infinity. Therefore, I do have an inflection point at 1 comma negative 7. And you would be really hard pressed to come up with all these points if you just graph points randomly. But by techniques of the calculus, we can find where's the highest point, where's the lowest point, where's the inflection point. Okay, so here's the whole graph. We had negative 1 comma 9 as a relative maximum. It is not the absolute maximum. There is no absolute maximum. But relatively speaking, in a small neighborhood of this point, it's the highest point. Slope is 0 right there. 3 comma negative 23, relative minimum or local minimum. It's not the lowest point on the whole graph. There is no absolute minimum, but relatively speaking, if I only look at a small neighborhood, right, just in here, it's a low point. And my inflection point is 1 negative 7. And by the way, you probably notice some of these numbers get super big. Don't bother to, go 1, 2, 3, 4, 5, 6, 7 off to negative 23. That takes too long. Just get the general relative position like so. Right, so here we go. Increasing to negative 1, decreasing to 3, increasing after 3. So up, down, up. Concave down from negative infinity to 1. So right up to here, upside down U shape. The rest of the time, U shape. Everything over here. Okay, so that's what we're up against. This is a typical curve sketch problem. So we're just going to look at more and more examples of this. And by the way, some of you out there may be saying, this takes too long for a 1 hour test. I understand that. I realize that. So whatever I give you on the test, either it's easy enough that you can do the whole thing fast enough, or I only have you do just a certain part of it. Like I might say, okay, just do the first derivative test, or only do the second derivative, but don't keep going, or maybe don't graph it, and so on. Okay, but for now, we're going to try to do the whole works for practice. Right. So first derivative test, second derivative test. Okay, and that tells us stuff like increasing, decreasing, right? Concave up, concave down, which way is the shape going? Okay, and again, people who build roads, people who build roller coasters, right? Where do we want our high point? Where do we want a low point? Where do we want concave down? Where do we want concave up? And so forth. Okay. All right, and let me do my focusing thing again since I'm done with that page. Now, so there's all that. And some more there. Okay. All right, next one I was going to do is I'm going to jump all the way to 37. It's another problem that's somewhat similar, but I said, what about all the problems in between? Don't worry, I'll come back to them, but there's a method to my madness. I want to do similar types of problems first. So way over 37 on page 302. Okay, f of x equals x cubed minus 12x plus 2. Okay, so look above. A, intervals of increase and decrease. B, local max and min. C, intervals of concavity, inflection points. Okay, and then D, sketch the graph. And never mind about checking your work with a graphing device. If you have one, great, but let's assume that we don't. Okay, x cubed minus 12x plus 2. All right, so again, the normal game is you start off by taking 2 derivatives and then factor if possible. Okay, so f prime, 3x squared minus 12. Factor out the 3, x squared minus 4. Factor further, 3 times x plus 2, x minus 2. Second derivative, 6x. All right, so normally then you set the first derivative equal to 0, do your sine chart. And then you do the same thing for the second derivative. Set the second derivative equal to 0, do your sine chart. All right, so set this equal to 0, that's easy, plus or minus 2, right? So x is plus or minus 2. I'm going to plot these points, so that means I need the y coordinate. So how do you find the y coordinate? Plug into which of the 3 functions, original, f prime, or f double prime. Which one is normally y? Y is the original. So put 2 back here. 2 cubed is 8. Minus 12 times 2 is 24, plus 2. Okay, and that works out to be negative 14. Again, I'll save time on the computations. You can do this as well as I can or better. Okay, but since I already did, I'll just go right to it so we can spend more time with the theory. Okay, I need f of negative 2. So plug in negative 2. Negative 2 cubed is negative 8. Negative 12 times negative 2 is a positive 24. And then plus 2, grind it out, 18. So my critical points are 2, negative 14, and negative 2, 18. Do my sine chart. Y prime is 3 times x plus 2, x minus 2. So on my number line, I lay down the critical points. Okay, so what's a critical point? Wherever the derivative is 0 or undefined. Most of the problems they aren't going to give you too many where the derivative is undefined. And our derivative was well defined, right? There's no trouble spots for the derivative. You're not dividing by 0. You're not taking any square roots or logs or trig. This is well defined. Any real number can be put in here. Okay, so negative 2 and 2. Now, when I plug in negative 2, I get 0, right? That's the idea. Put negative 2 here, you get 0. 0 times the rest of it is 0. Plug in 2 here and here. Here, 2 minus 2 is 0, so you don't care about the rest. That's going to be 0. That means everywhere else it is not 0. Not 0 here, not 0 here, not 0 here. Not 0 means positive or negative. So determine what's the sign, positive or negative. So pick something over here, here, and here. So what's over here? Negative 3. You could pick negative 4. You could pick negative 1,000,000, but negative 3 is the nicest. Between -2 and 2, I pick 0. Okay, I always suggest plug in 0 whenever possible. It makes the math much easier. Okay, although technically you could plug in, 0.3165214242828 or something like that, but that's crazy, right? And something bigger than 2, 3. 4 works, 5 works, a million works, but I like 3. And again, I just want the sign. 3 is always positive. So these pluses here represent the 3. Okay, -3 plus 2, -1, negative. -3 minus 2, negative. Positive times negative, positive. Plug in 0, 3 is always positive. 0 plus 2, positive. 0 minus 2, negative. Positive times negative, negative. This region is a negative. Okay, plug in 3. 3 is positive. 3 plus 2 is positive. 3 minus 2 is positive. So positive times positive times positive, positive. And we are doing the first derivative. First derivative positive, increasing, increasing. First derivative negative, decreasing. So intervals of increase and decrease. F is increasing from -∞ to -2. Union, U for union, 2 to infinity. That's where it's going up. That's where the roller coaster is going up. F is decreasing only between -2 and 2. Okay. Now, max or min, -2. I mean, these arrows almost tell you the way the roller coaster is going, right? I mean, look over here. See, I don't like roller coasters. Well, you're driving or you're on a bus, okay? The bus goes up the hill, then it goes down the hill. What does that mean about right here? Maximum. Relative maximum or local maximum at -2, 18. How did I get the y coordinate? Remember, you have to plug in to get the y coordinate. How about at 2? Okay. The roller coaster goes down, then it goes up. What happens when roller coaster goes down and up? You got a minimum. Relative minimum at 2, -14. Okay, so I don't have the concavity yet, but I do know that's a max, slope is 0. Minimum, slope is 0. Increasing, decreasing, increasing. Okay, we don't know the inflection point yet, but we'll get that shortly. So that's it for the first derivative analysis. And now the second derivative analysis, you pretty much do the same thing. Set the second derivative equal to 0, and then do a sine chart. Okay, so set y double prime equal to 0. You can say y double prime, f double prime, same thing. So where was my second derivative? 6x. 6x equals 0. Well, that means x equals 0. That's very easy. Plug in to find the y coordinate. F of 0, 0 minus 0 plus 2. 2. 0, comma 2. Might be an inflection point. It does not have to be an inflection point. It might be an inflection point. How do you know? There has to be a change in concavity. So let's do my sine chart again. I lay down a 0. 0 is the only number that will give me a result of 0, right? So pick something over here, something over here. This is so easy. I hope you think it's easy that you can get it right away. If I plug in any negative number, 6 times that is negative, right? I plug in -1. Plug in any positive number, like 1. 6 times 1 is 6, positive. All right. Negative second derivative, concave down. Positive second derivative, concave up. So intervals of concavity. F is CD, concave down from -∞ to 0. F is concave up, U-shaped from 0 to infinity. And I do indeed have an inflection point at 0, 2. Here's our graph. Completely analyzed. Okay. You can probably, those of you that like roller coasters, you've probably seen roller coasters that go like that. Okay. Just for increasing, decreasing. When is it going up? When is it going down? Increasing from -∞ to -2. There it is. It's also increasing from 2 to infinity. Okay. So maybe people who build the roller coasters, right? the ride, say, okay, we wanted to go up here, we want to go up here, and we want the roller coaster to go down here. So where's here between -2 and 2? Where'd it go? Yeah, right here. Function's decreasing from -2 to 2. So we want the roller coaster to go down here. Okay. Now, what about the concavity? We want concave down on this roller coaster between -infinity and 0, upside down U shape. After that, U shape. So here we go. Upside down U shape up until 0. Okay. Please notice that concavity has nothing to do with increasing or decreasing, right? Here it's increasing, here it's decreasing, but this is still considered upside down U shape, right? And then the rest of the time, concave up, U shape. Again, that has nothing to do with increasing or decreasing. Even though it's U shape, we would say this is decreasing, this is increasing. So there's our entire graph. Okay, there we go. Okay, and I'm finished with this graph, but I'll just mention quickly for those of you that like roller coasters. I'm guessing a lot of you like roller coasters. Okay, right here, it's the steepest negative slope. Okay, I don't know how to explain it, but you get a certain sensation, if you know what I mean. If you've been on roller coasters, when you get right to that point, right, the track is going like this, and then all of a sudden it switches back to concave up, so you kind of feel that sensation of changing and pushing over. For those of you that ride roller coasters, you know what I'm talking about. I don't ride roller coasters a lot, but I have been on roller coasters, put it that way. Okay. And for those of you who don't like roller coasters, maybe you don't get it, but there's a certain sensation you get when you switch from concave down to concave up, and vice versa. Okay, there's this a funny feeling when the track switches from that to that. And those of you who know what I'm talking about, because you ride roller coasters, that's sort of what's going on there. Okay. All right, so yeah, I'm giving a lot of roller coaster math, I guess. So there we go. All right, I'm going back to 13 now because I wanted to just do polynomials, but of course it's harder once you get it to trig. So sine x plus cosine x only from 0 to 2 pi. Okay, that's nice. But when you stop and think about it, the period of the sine function, 2 pi. Period of the cosine period is 2 pi. So once I get the graph from 0 to 2 pi, you can just copy and paste, right? The period was 2 pi, remember from trig, you can just take that graph and then paste, 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 and on the other side, paste, 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 right? So whatever the graph happens to look like, yeah, I'll show you quickly here. That's what the graph looks like. Copy and paste to the right and paste to the left forever, right? All right, well, they tell me to go from 0 to 2 pi. This is on a closed interval. Okay. Now they want us to analyze everything, but on tomorrow's quiz again, I'll give you something like this where just find the absolute max and absolute min on a closed interval. Okay, so this question asks more than I'm going to ask on tomorrow's quiz because I'm going to ask for, you know, all the concavity and intervals of increase and decrease and all that stuff. Tomorrow you just have to give me absolute max and min, which means you automatically have to plug in the two endpoints. Okay, so I plug in 0. Sine of 0 is 0, cosine of 0 is 1. So 0, 1. And since you know the period is 2 pi, when you plug in 2 pi, you're also going to get 1. Okay, so I automatically have 0, 1, 2 pi, 1. So right now for the graph, I have those two dots at the end, that one and that one. Okay, take two derivatives. So derivative of sine x is cosine x, derivative of cosine x is negative sine x. Second derivative, derivative of cosine x is negative sine x, derivative of negative sine x, remember negative means like -1, right? So the derivative is negative cosine x. Okay, set the first derivative equal to 0, set the second derivative equal to 0. They all pretty much work the same. Okay, cosine x minus sine x equals 0. Move this over. So you get cosine x equals sine x. Divide both sides by cosine x. I get 1 equals tangent x. Well, that's 45 degrees, pi over 4. And 225 degrees, 5 pi over 4. Okay, you're basically saying x and y coordinates are the same. That happens here and here. On a unit circle, you might recall both x and y are radical 2 over 2 right here. And over here, they're both negative radical 2 over 2. So when you divide them, the ratio, you get 1. So my critical numbers are pi over 4 and 5 pi over 4. Now you might say from trig, well, what about keep going around the circle and backwards? That's true, but they only want us to go for one period between 0 and 2 pi. So which is considered from 0 to 2 pi. Okay, I need the function values. So plug in pi over 4. Sine of pi over 4 is radical 2 over 2. Cosine of pi over 4 is also radical 2 over 2. So radical 2 over 2 plus radical 2 over 2 is 2 radical 2 over 2, or radical 2. It's about 1.4. And if you plug in 5 pi over 4, let's see. Yeah, that's negative radical 2 over 2, and that's also negative radical 2 over 2. So it's the same computation except negative radical 2 over 2. Negative 1.4. Okay, so now I do my sine chart. I lay down 0 and 2 pi, not because they're critical points, but those are the endpoints. Okay, so 0, 2 pi. And then my critical points were pi over 4, 5 pi over 4. Okay, so sine chart. I'm allowed to plug in 0. You don't have to, but 0 is nice. So plug in 0 to the derivative. Cosine 0 minus sine of 0. Cosine of 0 is 1. Sine of 0 is 0, 1. Positive. So plus here. Middle region. What's a nice number between pi over 4 and 5 pi over 4? Well, pi. Pi is 4 pi over 4, right? Plug in pi. Cosine of pi minus sine of pi. Cosine of pi is negative 1 from trig. Sine of pi is 0, negative 1, which is negative. So put a minus right there. And plug in 2 pi. Well, you already know when you plug in 2 pi, you get the same thing as if you plug in 0. So that's also going to be 1. Cosine 2 pi minus sine 2 pi, 1. Positive. Right. So once again, positive first derivative means increasing. Negative first derivative, decreasing. So f is increasing from 0 to pi over 4. These are all open intervals. They're not closed intervals. Strictly speaking, we're not increasing at 0 or at 2 pi or pi over 4 or 5 pi over 4. Okay. Union 5 pi over 4, 2 pi. F is decreasing from pi over 4 to 5 pi over 4. Okay. Tell me something about pi over 4. Max, min, or neither? Look at the graph. Look at the roller coaster. Up, down, maximum. How about 5 pi over 4? The ride, the bus goes down, then up, minimum. So I have a max at pi over 4, comma, radical 2, and a min at 5 pi over 4, negative radical 2. Okay. So here we are. There's my max, pi over 4, comma, radical 2. Here it's 1. There's my min, 5 pi over 4, negative radical 2. Right. So increasing up to pi over 4, decreasing to 5 pi over 4, then increasing. Okay. Now, how about which way is it curving? Concave up or concave down? Second derivative. Set the second derivative equal to 0. So where was my double prime? Where did my double prime go? It was negative sine x minus cosine x. Okay, set that equal to 0. Move negative cosine over. I get negative sine x equals cosine x. Divide both sides by cosine x. Actually, by negative cosine x, but it's the same thing. Tangent of x is negative 1. X and y coordinates are opposite. That's here and here, quadrants 2 and 4. So that's 3 pi over 4 and 7 pi over 4. Okay, ordered pairs here are negative radical 2/2, comma, radical 2/2. And here the reverse, positive radical 2/2, negative radical 2/2. Okay, what are the y coordinates? So I plug in 3π/4 to the original. Sine of 3π/4, radical 2/2. Cosine of 3π/4 is negative radical 2/2, that's 0. So 3π/4 is 0. I put inflection point here, but we'll get that later. We don't know that yet. And then 7π/4, sine of 7π/4, quadrant 4, negative radical 2/2. Cosine of 7π/4 is positive radical 2/2. Add them up again, you get 0. So 7π/4, comma 0. We don't know their inflection points yet, but we will shortly. Okay, so sine chart for a double prime. So put down 0 and 2π, 3π/4, 7π/4. Okay, so I picked 0. Negative sine of 0, 0. Minus the cosine of 0, that's -1, negative. Nice number in between. Again, I picked pi, 4π/4. Negative sine of pi, 0. Minus cosine of pi, -1, +1. That's positive. And we already know 2π is going to match 0, so -1, negative. Okay. Second derivative negative, concave down, CD here, CD here. So f is concave down from 0 to 3π/4, union 7π/4, 2π. The function is concave up, U-shape, between 3π/4, 7π/4. Do I have a change in concavity right here? Yes, I do. That means 3π/4, 0 is an inflection point. And do I have a change in concavity here? Yes, I do. That makes this also an inflection point. So here's the entire graph. Okay. I didn't write the points here because it would get too, crowded. But the maximum point, π/4 radical 2, high point, looks like it. Minimum point, 5π/4, negative radical 2. That's over here, lowest point. Increasing, decreasing, increasing, increasing, decreasing, increasing. So the roller coaster is going up to here, and then you go down, and you go up. Concavity starts off concave down up to 3π/4. So right up to here, inflection point, upside down U-shape. Then from 3π/4 to 7π/4, U-shape in between here. And then from 7π/4 to 2π, switches back to upside down U-shape. So there's our entire graph. Again, no doubt, those of you that like these rides, you've seen rides that go like this, right? Go up, down, and switch concavity, and go like that, and like that. Okay. All right, I'm done with that page, so let me do my focusing thing again. On that. And that. And that. Okay. All right, what time is it? 10 to? Okay, let's see how much time do I have for any more. So let me get started with something else. Okay, 25 and 24. I was going to do 24 also. It shows you all the possibilities. Okay, 25A. Sketch the graph of a function that satisfies all of the given conditions. F prime greater than 0, double prime less than 0. F is increasing. Remember, second derivative controls concavity. Less than 0 means concave down. Okay, so for 25A, increasing, concave down. 25A. Increasing, concave down. B, reverse, reverse. F prime less than 0, decreasing, concave up. So 25B, decreasing, concave up. Okay, and I'm going to do 24 also. Remember, F prime controls increasing and decreasing. Put it on your cheat sheet if you wish. Double prime controls concavity. Again, you should be fortunate that I'm giving you this cheat sheet, because if we were meeting face to face, I wouldn't give it to you. So you have to watch out in case your Calc 2 teacher doesn't let you have a cheat sheet. All right, so let's see. Decreasing, concave down. So 24A, decreasing, concave down. 24B, F prime greater than 0, increasing or decreasing? Increasing, concave up. 24B, increasing, concave up. Okay. All right, there we go. All right, what time is it? Let's see. I want to show you how to do one of these kind of problems, right? So make up a graph. I'll show you directions. Sketch the graph of a function that satisfies all of the given conditions. Top of 301. So all that stuff. F prime equals F prime of 0 equals F prime of 2 equals F prime of 4 equals 0. Okay, that means you have a horizontal tangent. Horizontal tangent means you might have a maximum, you might have a minimum. Increasing. X is less than 0 or between 2 and 4. Let's see what I have here. So at X equals 0, 2, and 4, you have a horizontal tangent. That's the interpretation of that first line. Horizontal tangent. F prime of X greater than 0. F is increasing if X is less than 0 or between 2 and 4. F is increasing from negative infinity to 0, union 2, 4. F prime of X less than 0, decreasing between 0 and 2, or X is greater than 4. Interval notation. F is decreasing from 0 to 2, union 4 to infinity. And then it says something about double prime. Double prime second derivative is concavity. So concave up between 1 and 3. F is concave up between 1 and 3. F is CD concave down if X is less than 1. Okay, double prime, negative, concave down. If X is less than 1 or greater than 3. Negative infinity, 1, union 3, infinity. Okay, so how do I put all those pieces together? So I did something like this. Ignore the graph for a moment. Increasing from negative infinity to 0, also from 2 to 4. Decreasing from 0 to 2 and 4 to infinity. Okay, pretend you don't see the graph. So it goes up, down, up, down. Okay, take a look right here. Up, down, that makes this a maximum. That's why I made a max. How about down and then up? Minimum. How about up and then down? Maximum. Okay. You say, where's the y coordinate? It doesn't matter as long as it's relatively in the right position. So that makes this a max, min, max. Okay, concavity, only concave up between 1 and 3. So between 1 and 3, I say to myself, okay, U shape. Everywhere else, upside down U shape. So here we are, upside down U shape, upside down U shape. So there's my graph. You just take all the pieces and analyze it from there. So let's see if we satisfied everything. Increasing, the roller coaster ride's going up to 0. Then between 0 and 2, it goes down. Then between 2 and 4, it goes back up. And the rest of the time it goes down. How is it curving? Okay. Concave down all the way up to 1. And please notice that concave up and down doesn't have anything necessarily to do with increasing, decreasing. Here we have increasing, decreasing, but it's still concave down, upside down U shape. Then the roller coaster switches to U shape between 1 and 3. And the rest of the time, it's upside down U shape. So there we go. Okay, so I see we're just about out of time. Let me just do my focus job. But you can see what's involved in a lot of these problems. Okay. And again, you might say, this takes too long to do on a test. Yeah, and I get it. So whatever I give you in a test, I might have you just do a part of, the whole thing. I mean, it's good for you to practice the whole thing, but I might only just ask you a small portion of it when it comes to the real exam. Okay, so we're out of time, folks. So tomorrow we're going to continue on, and after a certain amount of time, I'll stop and give you a problem, like I said, from the absolute max and min on a closed interval for the quiz tomorrow. So that was back in 4.1. Stuff like 47 through 61. Okay, and the procedure was just the closed interval method on page 281. Okay. All right, so that'll be for tomorrow quiz. All right, so that's about it for today, folks. So have a good day, and we'll see everybody next time. Okay, bye, everybody. Anybody who came late, put yourself in the chat.